All right, so this is a non-relativistic gauge theory, and you might think actually for a minute, if you think about it, that you've studied non-relativistic gauge theory before, because that's what you study when you study quantum mechanics. You're studying non-relativistic gauge theory, which is QED. So I want to spend this lecture talking about the relation between the Schrodinger equation in quantum mechanics and our NRQCD. So we'll make the title NRQCD and the Schrodinger equation. OK, so let's first of all just remember what the Schrodinger equation is. And I'll write it in momentum space, because that'll be sort of the most convenient way of making the comparison. So in momentum space, if we have a momentum space two-particle wave function, which I'll call psi tilde, and it's a function of energy and 3 momenta, the Schrodinger equation says that E minus p squared over 2m, which is the gradient squared over 2m that we usually have, is equal to the potential times the Schrodinger equation back again. But in momentum space, this becomes a convolution instead of a product. So we have our Coulomb potential, and it's a function of p minus k. And then it's times the wave function. But now the wave function is energy E and momentum k. OK, so that's our non-relativistic Schrodinger equation. And if we go through the power counting here, we could do that. And so let's not power count the wave function, since it appears on both sides. The E minus p squared over 2m, that's of order v squared. And here, this d3k, that's a v cubed. And this v Coulomb, if we think about how it power counts, it's an alpha over k squared. So it's an alpha over v squared. So that product is alpha times v. And we see that if alpha is of order v, that these two are the same size, which is what we expected from our power counting that we talked about in the last lecture. OK, so this is the non-relativistic Schrodinger equation. How does that relate to what we have in the quantum field theory? Well, in the quantum field theory, we have diagrams like the Coulomb exchange that we talked about in the last lecture. But we also have loop diagrams. And so let me spend a little bit of time talking about the following loop diagram, where we have 2 Coulomb exchanges in a box like this. And I'll label the external lines here E over 2 p, E over 2 minus p. This will be E over 2 p prime, E over 2 minus p prime. So the particle and the antiparticle. And then in the loop, I'll let this be E over 2 plus k. And so what that means is that this line is coming k minus p. And then down this line will be k minus p prime. And then down here, we'll have E over 2 minus k. OK, so that's the routing for the momenta in this loop diagram. And just like in the non-relativistic contact interaction case, here we can do the energy integral, the k0 integral, because these two propagators, these purple propagators, don't depend on k0. So we do the k0 by contours. So we have, in d dimensions, a d minus 1 dimensional 3 vector type integral. And then we have the 2 potentials. We're still left with them. So this is v Coulomb of k vector minus p vector, and v Coulomb of k vector minus p prime vector. And then downstairs, we get the 2-particle propagator, which is E minus k squared. And if we want to be precise, it would be the reduced mass that shows up there. OK, so that's the type of integral that we're finding in this situation. So how does that relate to the Schrodinger equation? It doesn't seem obvious at all. In order to see how this relates to the Schrodinger equation, I want to look at, instead of the wave function, the Schrodinger equation for the Green's function. And we'll see that that is related to this integral that we just set up here. So the claim is that the Schrodinger equation for the 2-particle Green's function is related to the following series of diagrams. So we could have no exchange. We could have a single exchange. And then we could have 2 exchanges, et cetera. So let me draw one more. 3 exchanges. And actually, the Schrodinger equation is going to be related to the sum of these diagrams, where I sum up these ladders to all orders in perturbation theory. So it's a series of diagrams in the quantum field theory that's related to what you're getting out of solving the Schrodinger equation. That's my claim. So now let me show you that that's true. So let me write down the analog of this equation up here, but for the Green's function in the quantum mechanics. So that would be the following equation. We have E minus p squared over 2m. And then this is a momentum space Green function, so I'll call it G tilde of E p prime. There's a term that's related to just a kind of what every Green function has, which is just a delta function. And then there's a term that's coming from the source with the potential. So this is the sort of the thing that the Green function has that the wave function doesn't. And then we have a d3k vector of p minus k. And that's kind of like the wave function, where we have the Green's function back again. But now this is k p prime. So that's the Schrodinger equation for the Green's function in momentum space. And in order to relate it to these diagrams, I'm going to define a slightly different Green's function. So I'll define a Green's function h, which is, again, has the same arguments. And it's just obtained by g by multiplying on both sides by one of these propagator factors. So I have an e minus p squared over 2m, and then the g with the same arguments, and then an e minus p prime squared over 2m. And so I can rewrite this equation here that we have for the Green's function g back in terms of an equation for the Green's function h. And so I'll skip the math and just tell you the answer. So when we do that, we have an equation that says h of p comma p prime. And I can put everything on the right-hand side now. It'll still be integral differential equation, an integral equation in momentum space. So h will appear on the right-hand side here. The source term, the delta function term becomes that. And now, because of this change, when we write things in terms of h, the propagators are now showing up downstairs instead of upstairs, because we've sort of switching from a g to an h, you get extra propagators downstairs. Let me try to follow my notation where I put the e first. Now we have a propagator downstairs. OK, so that starts to look kind of promising, because we're getting the same type of propagator that downstairs as we had over there. And actually, we can solve this equation. One way of solving it is to generate a series in the potential by just iterating the equation and sticking the delta function in here, and then getting the next term and solving it in an iterative fashion. So let me expand it out and solve it in that way. So the first term is just our delta function term, and I'll just write it again for completeness. The next term, if we stick that delta function in here, you can see that it's going to collapse the integral, because I can just do the integral with the delta function. The 2 pi cubed will cancel the 1 over 2 pi cubed that's implicit in my d slash here. The e minus p squared over 2m, once the e is set to k, will cancel this denominator. So all I'm going to be left with is the potential. So the next term in the series is just one factor of the potential. And then if I keep iterating it again, I'm now sticking the potential back in. And it's at this order that I see what we had over there. So when I stick this back in, I have my potential, and then another potential, which of course is symmetric in its argument, and then e minus k squared over 2m. And then I could keep going and keep improving the iterative solution. And this has a one-to-one correspondence with the diagrams we drew over there. So sort of for completeness, let's just draw it. This is no scattering. There's no potential there. This one here has a single potential scattering between the particles. This one here is exactly our box diagram. And then the higher order terms would be contained in the dots. And if I keep going, The next term I would find would be, for example, this double box loop diagram, and then higher order terms. So indeed, these diagrams exactly encode this two-particle Schrodinger equation, and that's the correspondence between the quantum field theory and the non-relativistic quantum mechanics. You can ask about maybe what happens with cross-box diagrams, but that's just like what we talked about in Eqtn as well as in non-relativistic field theory. Those diagrams vanish because you can't, when you do the K0 contour, the poles are on the same side, and you just get 0. So it's really only these instantaneous interactions in these box-type diagrams that are relevant for this correspondence with the quantum mechanics.